Hello everyone. Welcome back to Introduction to Semiconductor Devices. So in the last couple of lectures, we have understood how a MOSFET functions, and we have also derived the current voltage characteristics for a MOSFET. So we've seen that a MOSFET, if you look at the vertical direction, in the sense, if you look at the gate oxide and the semiconductor, it is essentially a MOS capacitor. So we have studied the electrostatics and of a MOS capacitor in great depth, and then in the lateral direction from source to the drain, it is essentially two PN diodes which are back to back, right? So we have seen how there is a barrier formed across a channel, and because of which current will not conduct, and that barrier can be changed by applying a gate voltage. So this is essential physics of the MOSFET. Okay. So today we would like to understand what makes a good MOSFET. Okay. So MOSFETs are used in a wide range of applications, and to understand what is a good MOSFET, we need to examine its current voltage characteristics in great detail. Okay. So to start with, so what you're seeing here is basically a symbol, circuit symbol for a MOSFET. This is one of the symbols. So this is on the left, it is an NMOS device. On the right, it is a PMOS device. These are one of the representations. There are multiple representations. If you look at different textbooks, they'll have different notations, but you can refer and then compare that. Okay. So when you have a MOSFET, there are two types of IV characteristics that we are interested in. So we've already seen, that there are 4 terminals in a MOSFET, and I'm only showing you 3 terminals here, but there is always a bulk, and we know what to do with the bulk already, right? So if you look at this particular picture, there is a drain, there is a source, and there is a gate, right? So usually for an MOSFET, we will ground the source, and we can apply varying voltages on the drain and the gate. So in this case, I'm showing you that the voltages are changed in the range 0 to VDD. VDD is commonly used notation for supply voltage. So each technology has a different supply. It can have a different supply voltage. So the maximum voltage, sort of, you could think of it like that. Okay. For example, in the old TTL logic, we used to have supply voltages as 5 volts. And then that came down to 3.3 and then 1.8 and then 3.3, 2.5, 1.8 and 1. So nowadays it's usually around 1. Okay. We will explain why that happens also in the next week. Okay. So now what we are considering is you could sweep the drain voltage from 0 to VDD, or you could also sweep the gate voltage from 0 to VDD. So when we do this, we get 2 types of characteristics. The first type is what we call as output characteristics, which is essentially a function of a plot of drain voltage versus drain current. Okay. Sometimes we also call this as ID/VD characteristics. Okay, drain current and drain voltage characteristics. And we have seen this in detail. We fix a particular gate voltage and then sweep the drain voltage from 0 to the maximum number. Okay. So while we do that, we saw that when the drain voltage is small, your MOSFET is biased in linear regime, and then as you cross VD-SAT, which we said is equal to VGS minus VT. Okay. If your drain voltage is greater than VD-SAT, we said the current saturates. Okay. So I have shown here 2 particular graphs. One is basically when your gate voltage is less than VT, we don't expect current, right? The transistor is off. So no current, but then if you increase and let's say you choose VGS equal to VDD, you get saturating current characteristic, which is shown here. Okay. So it's important to note that on the left of VD-SAT, it is the linear regime. On the right, it is saturation regime. Okay. This is one type of characteristic which we call as output characteristics. There is also one more type of characteristic which we can measure, which we call as transfer characteristics. In this case, we will keep the drain voltage fixed, okay, and then sweep the gate voltage. Okay. So when we do that, we can choose the drain voltage to be a small number, like 50 to 100 millivolts, And if we do that, that MOSFET will be biased in the linear regime. So you get a linear transfer characteristic, okay, which is shown in the bottom here. And then you could also choose the drain voltage to be at supply voltage, VDD. If we choose that, then definitely the VDS is going to be greater than VDSAT. And that's why the MOSFET will be biased in saturation. So you get a saturation ID, IDVG curve. Okay, this we call as IDVG. These are different ways of referring to it. So in transfer characteristic, we are fixing VDS and then sweeping VGS, gate voltage. In output, we are fixing VGS and then sweep VDS. Okay. So these characteristics, you can actually do the measurements at multiple VGSs or VDSs. So then you get a family of curves, like what we have seen in the last lecture. We showed you that there will be a quadratic relation like this, right? Drain current is going to increase. Like as your gate voltage increases, the drain current increases, and there's a quadratic behavior in the saturation. That's what we said. Okay, we get a family of curves. So this is for an NMOS device. You could also do it for a PMOS device, and we said the PMOS device is essentially a complementary device to NMOS. One thing to kind of note is in CMOS technology, especially, we tend to connect the source to the highest supply voltage, highest voltage, which is usually the supply voltage. Okay, so source is connected to VDD, and then gate is swept from 0 to, let's say, VDD, and drain can be swept from 0 to VDD. Why do we do this? Well, one of the reasons is that we are using an N-type substrate. We want to make sure that the source and the channel junction is always reverse biased. Similarly, the drain channel or drain bulk junction, right? That is also reverse biased. So since it's an N-type substrate, we connect it to VDD, so it gets reverse biased. We don't want to accidentally forward bias the source channel or the drain channel junction. Okay, that's one reason. The other reason is it makes it very convenient. We said the gate voltages and the drain voltages for a PMOS device are exactly complementary. So for NMOS device, they were positive. For a PMOS device, they will be negative. If it's a well-designed PMOS device. Okay, so these can be tuned by adjusting parameters like work function and doping and things like that. Okay, so if you take a well-designed complementary PMOS device, what will be the VGS in the way that we have bias here? VGS, let's say, is going to be, if the gate voltage is 0, then it's going to be minus VDD, right? VGS is 0. Sorry, VG is 0. If I apply 0 volts to the gate, then I get VGS related to the source. We get VGS to be, I'm sorry, then I should not write this as 0 to VDD. I should say that this is only VG and this is only VD. Okay. So if I say VGS, I'm referring it, related to the source. Okay. So, and then if I keep my gate voltage as VDD, then my VGS is going to be 0. Right. So by tying the source to the VDD, we are essentially sweeping the gate voltage from 0 to minus VDD. Same thing happens to VDD also, VDS also. Okay. When VD is 0, then VDS is minus VDD. When VD is VDD, then VDS will be 0. Right? So we are essentially sweeping in the negative sense without actually having to create another voltage source. Okay. Otherwise, you have to have one voltage source which is going from 0 to VDD, other one going from 0 to minus VDD, and so on. So we can avoid that. So this is the way it is used in the CMOS devices. Okay. All right. So fine, we can measure these characteristics for NMOS and PMOS devices. But what are the metrics that we need to look for when we think about a MOSFET? Okay. To understand that, let's look at the drain characteristics. Okay. So what we did here was we swept VDS from 0 to, let's say, VDD, and you chose some VGS. Okay. Initially VGS of 0 and less than VT and VGS of VDD. So one of the important metrics in a MOS device is the input resistance. Okay. How much will be the input resistance of the MOSFET? Well, the input now, VGS, gate is the input where you are actually using. So MOSFET is a voltage controlled current device, because you're applying the gate voltage and you're controlling the current in the drain source nodes. Okay. All right. So what is the input resistance of a MOSFET? Well, we said that the gate is actually having a metal, and then there's an oxide which is separating. And the oxide is an insulator. It's a very good insulator, supposed to be a very good insulator. So usually the input resistance of a MOSFET will be typically 10 power 9 to 10 power 12 ohms or tera ohms range. It's a very, very good, it has a very high input resistance. So usually it doesn't create a problem. Okay. And this is because because of an insulating gate oxide. Okay, so it has a very high input resistance. That means if you take another voltage source and apply voltage, all of the voltage will fall across the MOSFET. Okay. Or another MOSFET could be driving it. In that case as well, most of the voltage will fall across the MOSFET in consideration. Okay. All right. This is one of the parameters. The other important parameter is an output resistance. How do we define output resistance? Okay. Well, output resistance is defined as derivative of VDS with respect to ID. Let's say this could be at a particular VGS. You fix a VGS and then calculate the derivative, and then you get the resistance, output resistance. So if you are in the linear, of course, I mean, if your gate voltage was slow, the drain voltage was low, then you are in the linear regime and there's a constant resistance. But usually the MOSFETs are biased in saturation. In that case, you see that the ID is not changing very much for some change in VDS. So we can expect that the resistance is quite large. Okay. Sorry, quite small. Output resistance is quite small, right? Because the current is not really changing much. Okay. So you can see that because the slope is nearly zero. Let me see. The current is not changing. Yeah. Sorry, yeah, it's actually high resistance, right? Because the current is changing by a very small amount for a large change in VDS, right? So it's like a current source. Okay. MOSFET behaves like a MOSFET is a current source. What is the characteristic for current source? Irrespective of your load, it should supply the same amount of current, and it does that when its output resistance is large. Okay. So you could also see that, like, say, by very small change in the drain current compared to large change in the VDS. That's why it is larger output resistance. Okay. But then what happens is, this is for an ideal MOSFET. In the square law theory we saw, right, that once the MOSFET hits saturation, it sort of remains constant. And we said the constant current was ID. ID was mu Cox W by, let's say, 2L into VGS minus VT whole square. We said the current remains at this value. But it turns out that this is not quite true. There is some small change in the current. Small increase in ID with VDS increase. Okay. So this happens because of a short channel effect, because of what is known as channel length modulation. And this channel length modulation becomes more and more significant in the short channel devices. We will talk in detail about it in the next week. Okay. So for now, essentially what we're saying is there is this large output resistance and large input resistance. Okay. Realistic devices have a finite output resistance. All right. So what are the applications that we can use MOSFETs? Okay. So we can use it in analog circuits. And we can actually think of a small signal equivalent circuit in analog circuits. Okay. What we can do is, let's say here there is this MOSFET, and we applied a voltage VDS and then gate voltage VGS. So you could have a drain current, which is ID, which is essentially a function of VGS and VDS. Right. So this is, you could fix these DC voltages. and then you can get a DC current. And then you can apply a very small signal on top of this DC. So for example, I can modulate the VDS by applying a small signal VGS. Here, sorry, this is VDS, small VDS, AC signal I can apply. Similarly here, I can apply a small AC signal of VGS. Okay, so this is AC signal. Okay, so what happens when I do this? Okay, that's what we are interested in finding out. So we can say that let's say ID. Now I'm applying a DC VGS plus AC VGS, comma, let's say VDS plus AC VDS. This is what we are applying. So if this is a current, we can write this as essentially equal to ID, which is a DC operating current, plus there's a small ID which I'm calling as AC drain current. AC drain current, you have a DC operating point. So essentially my AC is going to modulate my current. How much is this? This we can actually write out by Taylor series. You can expand this particular term by write out a Taylor expansion for this, and it will turn out to be ID at VGS and then VDS. This is the DC operating point, plus the small change in the gate voltage will give you a current which is proportional to the derivative, right? So dID by dVGS, I should write it as capital VGS, VGS into VG, yes, plus, so at this actually I'll do it at a constant VDS constant. Okay, and then I can write out another derivative, partial derivative. Okay, I should write this as partial derivative. Well, since I'm taking it as constant, I could, there's no big difference. Okay, so partial derivative of ID with respect to VDS at VGS constant. Okay, and then there will be a small signal VDS. So this is your Taylor expansion. What this is telling you is that by comparing, I can call this as equation 1 and then I can call this as equation 2. By subtracting, what essentially you get is ID, the small signal current, is going to be equal to ID by VGS at constant VDS times VGS plus partial derivative of ID with respect to VDS at constant VGS and, sorry, this is not VDS. Okay, so this is a very interesting thing, because whenever you have an AC voltage that is applied to either gate or drain, the impact on the drain current can be calculated by knowing two parameters, which are essentially derivatives of the IV characteristics. Okay, and these two parameters are very crucial, so we give them a separate name. So this particular term is called as transconductance. Transconductance, and we give it a name GM. Okay, so, and this is, if you notice it, okay, yeah, this is transconductance. We will derive an expression for it in a moment. And the other term is output conductance. Okay, and we'll call it as GD. And this, if you notice, this is a derivative of ID with respect to VDS. So this is exactly the inverse of the output resistance. So this is 1 over output resistance. Okay, it's going to be very small. It's negligible in many cases. Okay. But we could calculate. I mean, depending on how the slope of the IV characteristics is, we can find out how much is the output conductance. Okay. In small channel devices, it's going to be some finite number. What about transconductance? Well, transconductance we can calculate. We can write out an expression for drain current. We said already that drain current was, sorry, ID was mu Cox W by L VGS minus VT times VDS. Right? This is the linear current, linear drain current, right? The linear regime. Okay. So if your MOSFET is biased in the linear regime, what will be the transconductance? Well, GM is going to be, I'll say GM, I'll also mention linear, just to mention that it is in the linear regime. The transconductance is going to be the derivative of it. So basically mu Cox W by L times VDS. Okay, because we are calculating that at a particular VDS. Okay. So here you see that the transconductance is function of, this is linearly dependent on, linearly varies with VDS, does not change with current, okay? Does not change with VGS, okay? So this is the linear transconductance. You could also have the saturation transconductance. So ID in the saturation regime is going to be mu Cox W. Remember there's a half, so I'll just put it as 2L VGS minus VT whole square. Okay. So what happens now to transconductance? Well, GM saturation regime is going to be 2 will cancel out, so you get mu Cox W by L into VGS minus VT. This is what it's going to be. So here you see that this is linearly increases with VGS and constant with respect to VDS. Okay. So this is what it is. So I mean, depending on how the MOSFET is biased, you can have varying transconductance and output conductance and things like that. Okay. So these parameters are very, very important for analog circuits. Whenever you have some small signal circuit, small signal equivalent that you want to analyze, this is going to play a lot of important role. Okay. All right. But the MOSFETs are not really, we don't use them. We use them for analog designs like op amps, and so on. You can make a lot of circuits with op amps. I mean, you must be studying some linear integrated circuits where you have taken op amp and studied it in great detail. But if you look at an op amp inside an op amp, it is consisting of minimum there will be about 9 transistors, or it could go up to 27 transistors or so. You can actually have MOSFET circuits. You design the op amp, like 741 that you use in your linear integrated circuits course. Can be designed using techniques. There are a lot of design techniques that we can use, things like current mirrors and so on, and then we design that. So that's a completely different specialized course that will follow this if you're interested in that. Okay. But that is in the domain of analog IC design. Okay. You could also have, most of the MOSFETs are used in the digital applications. For example, your processors it's a digital device, right? Digital processor, because you have zeros and ones. You're not really concerned about how the voltage is changing continuously from 0 to VDD. So in digital circuits, we refer to as 0. Logic 0 is basically 0 volts. Okay, logic 1 I can refer to as VDD. Okay, so basically VDD, it could be, let's say, in the modern technology, it's about 1 volt. Okay? Or in the past, it was 5 volts, let's say. So if your voltage is 0, it's logic 0, 1, it is logic 1, right? So you can design digital circuits. So because of the switching from 0 to 1, you're able to do this, a lot of processing. All the digital circuits are essentially this, right? Boolean algebra we apply, and then we design circuits like, NANDs, NORs, and so on. So those are all digital circuits, right? So MOSFET is, most predominantly used in digital ICs. Okay? And in that, a MOSFET can easily be simplified and analyzed using what is known as a switch model. So we saw that when you apply a certain gate voltage above a threshold, the MOSFET conducts, okay? And we'll call it as on state, okay? So if I put my VGS greater than VT, so ID is basically some number, it's going to be some, ID is, let's call it ID naught, some number, okay? Or I'll call it ID on, okay? Ion is a better number, ion, when the transistor is on, okay? So specifically what I'll do is this is going to have VGS of VDD and VDS of VDD. If I put both my drain and the gate voltages at the supply voltage, then whatever drain current I get, I refer to it as I on. Okay, that is when the switch is on. When your VGS equal to 0, I'll call this as ID. I'll call this as I off. Okay, so essentially in a processor, like for example, Core 2 Duo processor in your computer, would essentially keep switching from 0 and 1. Okay, so current will switch from ion to I off to ion. Okay, this is the switching. So that's what is represented here. By if you flip the switch, you have the current path which is formed. So you have current flow from the whatever drain terminal to the source into the ground. Or if it's open, then there's no current flowing. That's what we try to show by the switch model. Okay. It's of course a simplified model. The realistic cases will be slightly more complicated. But anyway, for our practical purposes, it's okay right now to consider this. So how much is this, current? Okay. To analyze that, here I'm showing you the transfer characteristics, but with the ID in a log scale. Okay, so it's same ID that we have seen in the past. In the last 2 slides back, maybe you saw that the current voltage was increasing. The current is like this ID versus voltage VGS, right? This is VD. So there's an exponential increase in the current, drain current with respect to VGS. And it is not quite surprising if you think about it. No? So what is the reason why how the gate is actually controlling the drain current? Well, we have drawn this, always you should go back and remember this physical picture wherein you have a Fermi level which is constant, and then you have the source and then the drain, and in between you have the channel, right? So we saw that there was a barrier that is forming here. This is a potential barrier because the current, the electric field here is going to be in this direction, and the electric field is here in this direction. So electrons cannot enter into the channel, so there's no current flow. And this barrier is what dictates your current flow. So when you increase your voltage, gate voltage, for the positive direction, you're lowering the barrier. This is for an NMOS device, right? And in the opposite case, when you decrease it, it actually increases the barrier. And this, we saw that whenever you have current flow across a barrier, like for example, a PN junction is the simplest case. You saw that the current was, if I write out an expression, it was J equal to J naught exponential QV applied by KT. Actually, I should put a -1 here. Okay, yeah. So this is what the current was. Right? Whenever you have a current flow across a barrier, so it will depend on the barrier height. Okay. So now, what you say is, if you have such a phenomenon, it is very useful to draw the transfer characteristics in a log scale. So what we are showing here is, initially, once above a VT, there is going to be some change, and because it's a log scale, it doesn't seem like it's a lot, but there is a significant increase in the current. But in the past, whenever we showed the IV characteristics, we did not really emphasize this part. We didn't know what is off current here. How much is it? That's important, right? So to emphasize the off current, we show the IV characteristics in the log scale. When we do that, when VGS is 0, let's say there's going to be some number, some current here, which we call as off current. Okay. And when VGS is VDD and VDS is VDD, we call it on current. Okay. These two numbers are very, very important for digital circuits. So we have a, what we call as a figure of merit. You could take a ratio of I on to I off. if you this ratio plays a very crucial role whenever there is a new technology that comes up. Let's say, Intel is introducing, let's say, 7 nanometer or 5 nanometer technology. They'll talk about this because this ratio should be high. If it's high, then it's a good technology. And what is a typical number? No, I mean, just, this ion is going to depend on various, geometrical parameters. For example, current is dependent on width, length, and so on, right? And there are also some, how effective the channel is in actually controlling that. So I'll just take a typical number and I'll say that, let's say it's about 10 power minus 4 amps. Okay, just, 0.1 milliamps, 100 microamps. Okay, divided by, let's say this could be even 10 power minus 10 amps. This is a typical number. This is 100 picoamps is not really a large current. Okay, for a single MOSFET I'm talking about. Okay, so what is the voltage? What is the ratio of the ion to I off? This is about, in this case, 6 orders of magnitude. Okay, so this is a large change in the drain current, and which is very, very useful for digital applications. Okay? We want this to be as high as possible, so that, because whenever you turn on the MOSFET, you want the current to flow. When you don't want the current, when you switch it off, you don't want any current to flow. Why? Because the moment current flows, you are consuming power. For example, if you're using a cell phone, whenever you're, you just put the cell phone on a table, you're not using it. But if, it's in the off state, the processor has to be in the off state, right? At least some of the circuits are in the off state. But if still, they still transmit current, large current, let's say, microamps of current, then you're going to bleed your battery, right? You're going to discharge your battery. So that is why the cell phones get discharged even if you don't use it. Of course, some of the chips are always on and they're trying to communicate with the cell phone tower and all that. That happens. But some of the chips are off and they should not discharge any current. But then in reality, there's going to be very small current that keeps flowing. It might be 100 picoamps per MOSFET. But then there are, let's say, 1 million MOSFETs in your cell phone. Then it becomes a substantial amount of current. And let's say the supply voltage is, I don't know, battery 1.8 volts maybe. And then you can compute, let's say there are 1 million transistors. So 1 million transistors will give you about 10 power minus 4. So 100 microamps of current. So 1.8 volt battery. So you can compute the power dissipation, the voltage into the current. That will give you the power dissipation. So it can be substantial amount of power that is getting dissipated. Okay. That's why when you're talking to somebody on a cell phone, the cell phone heats up because you're drawing current. Okay, that is causing power dissipation, voltage into current, right? 1.8 into, let's say, 1 milliamp. Okay, that's 1 milliwatt of power that's getting dissipated. It might seem like small, but then remember there are 1 million transistors. So it can be a substantial amount. Okay. So we always worry about the power dissipation whenever we are talking of mobile circuits, mobile chips. Anyway, so this is the application of a MOSFET in the digital domain. Okay. It is so important that we actually we define a parameter which we call a subthreshold swing to capture how the drain current changes with gate voltage. So subthreshold swing, SS I'll call it. So how ID changes with let's say gate voltage. Okay. So I already mentioned this to you, that let's say, this is current flow across a barrier, like a thermionic barrier. So you have J is going to be J naught exponential applied by KT, QV applied by KT, right? So this is the current, some current is flowing at some applied voltage, okay? Now we want to understand how much gate voltage change do we have to do to get 1 decade change in the current. For example, I want to make my current to be 10 times J. Okay. If I want to get this, how much should I apply? How much extra delta V should I apply to my gate? So I'll say QVA plus I'll say delta V by KT. I think I have mentioned this sometime in the course again. I'm just repeating it. So if you want to do this, so let's say this is 1 and 2, equation 1, equation 2. Take the ratio of these things. What you get is 10 equal to exponential Q delta V by KT. Okay. So this delta V, the gate voltage change, required to produce one order of change in the drain current is known as subthreshold swing. Okay. So I'll define subthreshold swing as delta V required to produce one order change in drain current. Okay, how much is that? Well, delta V is going to be, or no, I'll not call it, yeah, SS I'll call it. Subthreshold swing is equal to 10 times KT. No, 10, okay, so we have to take the natural logarithm of it. So it will be 10 times, so it will be 2.303 into log 10. Log 10 will be 1. So this will be, okay, of course, I could also put a non-ideality factor. Okay, I'm just going back and adding that. So basically in the diode conduction, there can be some non-ideality factor, which we call as N, right? I can introduce that as well. So this will be N KT by Q into 2.3. Okay. So this particular number, we have seen it many, many times. This is roughly 60 millivolts. Okay. And N is basically going to be between 1 and 1.5 in most MOSFETs, 1 to 1.5. Okay. So the subthreshold swing is a very, very important quantity, which we define as some number millivolts per decade. Okay. So how many millivolts of gate voltage change should be there to produce 1 decade change in the current? Okay. So that is what we are seeing here. So let's try to take an example and compute this. So this has implications when we talk about MOSFET scaling. That's why I want to emphasize this. Okay. Let's say I take my blue curve here. There are two curves. Now, one of the VD is one of the gate transfer characteristics is measured at VDS of 50 millivolts. Another one we are measuring it at 1 volt. Okay. This is this is experimental data, you could say. I mean, this is very, very close to experimental data. Okay. This is actually extracted from a model, but matched to the experiment. Let's take some numbers. So how do we compute this? Let's say I take 2 points on this. Let me take this point here. This is 1 point. So I'm taking my current to be 10 power minus 6. Okay. So I'll take this. This is 1 point I have. And then another point, I need to take 2 points to calculate the slope essentially. I mean, inverse of slope, it turns out to be. Okay. So here I want to do it from, let's say, this point. Okay. So this is 0.25 here. So I'll say this is 0.125 and this will be, I don't know, I'll just approximate it by 0.025. Okay. I'm trying to find out the distance here between these 2 points. X in the X direction, this is going to be equal to 125 and 25. So 150 millivolts, I'll say. Delta V, the change in the gate voltage required to produce this. I've chosen these points in such a way that I have now here the current is changing at this point. Current is at this point, the current is 10 power minus 8. Okay, this is, let's call it as P1 and P2. I chose 2 points in such a way that at point 1, the current is 10 power minus 6 and point 2, then it's 10 power minus 8. So there is 2 orders change in the current. And then I'm trying to find what is the corresponding change in the gate voltage. So the gate voltage change is 150 millivolts. So this is divided by 2 orders, right? 2 decades, I'll say. So your subthreshold swing, SS, is going to be 75 millivolts per decade. Similarly, you could do one more problem wherein you take the red curve now. Let's say I'll take 10 power minus 5 as the first point. This I'll call as P1, and then I'll take maybe this point. This as P2. Okay, so this entire distance is basically, this is 0.25. I don't know, this is definitely greater than 0.125. Maybe I'll call it 0.3 or 0.4. Maybe I'll take this as. sorry, not 0.3, yeah, 130, 140 millivolts, maybe, right? The distance is 140 millivolts, I'll say. And then in the y-axis, this is 10 power minus 5, and this is 10 power minus 7. So there's again 2 orders change. So there's 2 decades change here, 2 decades. So this is again 70 millivolts per decade. Okay. So this is a very, very important parameter that controls. Ideally, if you have a MOSFET, ideal MOSFET, you would like this to be 0. So that just below VT it is off. Current should be completely 0. But in reality, if you use the regular, this sort of a junction, current flow across the junction sort of a configuration, you will get, classical MOSFETs can have classical MOSFETs, like what we have been discussing so far, right? Have SS minimum, okay, of 60 millivolts per decade. This is the minimum that you can get. Okay. Essentially, what we are saying is we are not able to turn off the drain current easily. We have to change a reasonably large, 60 millivolts. If you, let's say we want as high ion to I-off ratio, right? We have to make ion very, very small. Let's say I want to decrease my I-off by 5 orders, or so when I switch it off, let's say initially the I-on was 1 milliampere. When I switch it off, I want it to be 1 microampere. I want 3 orders of change in the current. How much should I change my gate voltage? I should change it by 3 orders, so 3 decades. So it will be 3 into 60. That is a minimum possible voltage. At least I have to apply 180 millivolts. Okay, but 3 decades is not enough, nearly enough for us. We want it to be changing by 6 decades, let's say. So I want to take my 1 milliamp to 1 nanoamp. If I want to change that much of current, 6 orders of magnitude change in the current, then I need to apply 36 0.36 volts. Okay, 360 millivolts I have to apply. Only if I apply, 360 below VT, I'll go to 360 millivolts below VT. Then I'll have my MOSFET switched off completely. Okay. It has a lot of implications. I'll discuss this further when I talk about scaling. Okay. Well, yeah, this is basically about a summary of various metrics that are important. Of course, there are these VD-SAT, which is a very important term, which I didn't mention, but of course, VT is important, VD-SAT is important. The drain current at the saturation is very important. So these are different metrics that we use when we want to compare different MOSFET technologies. Okay. So I would like you to spend some time analyzing this. Okay. So please make sure that you understand how these parameters are computed. We'll give you some problems in the assignment that will also help you get a better hang of this. All right. So, so thank you very much. So, so far we have understood the basic operation of MOSFET. So I'll also record a short video on fabrication, maybe 5-10 minutes video, just to talk about how these things are fabricated. Then in the next week, we will talk about Moore's law, and then scaling and so on. Okay. All right, I'll see you there. Thank you so much.